Hello everyone, my name is Sherwin and I will be explaining the magic square problem from IEEE Extreme 8.0 today. So let's take a look at the problem. The problem simply asks to calculate the sum of the columns, the rows, and the diagonals, as well as the anti-diagonal, and compare them together. That's pretty much the whole thing we have to do. If you need to take a look at the main problem, it doesn't have a long story behind it, just a few lines, and pretty much just asking to calculate all of these sums and then compare everything to the main diagonal and print out the ones that do not match. And the way to print them is to print the indexes according to the given indexing, which is everything starts with the last column with negative numbers, comes all the way back to -1 for the first column. Then the 0 index is given to the anti-diagonal, and the positive numbers are given to the rows in order. Now, after finding the ones that do not match, we just have to print the ones that don't match in a sorted order, in fact. So the logic is to simply the first thing that comes to mind basically is to simply calculate all of these sums and compare them together. Now let's call the first sum, which is the one we have to compare to the other ones, the sum. This one can be calculated very simple, just with a for loop. Just go through all of the elements of the main diagonal and then sum them up. And then we keep that value as a separate value, and then we do the same thing for all of the rows, columns, and the anti-diagonal, and then compare them to this dsum value. If it's not matching, then we will just keep that index for printing it later on. Yeah, that's pretty much it. Now, the next question would be, is this algorithm, the naive algorithm, fast enough to get the answer within 1 second or so, which is the time limit of the solution? So, to that end, we have to calculate the complexity of the problem. Now, we have an n by n matrix. We want to calculate a bunch of summations. Each of them has O(n) complexity because we are summing up over n terms, and then the number of summations we have to calculate is 2n plus 2, n rows, n columns, and 2 diagonals. Now the output should be sorted, so in case the output is not generated in a sorted fashion, then we have to sort out these elements, which is at most 2n plus 2 or 2n plus 1 if you don't count the main diagonal, which ends up being O(n) log n. A good sorting algorithm can be O(n) log n. So the overall complexity adds up to be O(n) squared. Now, there is this rule known as 1 billion rule, or it might be known under different names, that roughly says keep the number of calculations below 1 billion. Otherwise, there's a chance of getting a time limit error. This rule is very useful for any online contest. Usually the online contests give you a few seconds of CPU time for running your code, and basically 1 billion roughly gives you 1 second. So if you want to see how many operations or how many calculations we have in this algorithm, keeping that in mind that n is given to be less than 1000 in the problem over here. So we are supposed to do about n square number of operations, so we end up doing about a small factor times 1 million, which is much smaller than 1 billion, so we're good to go. And one last trick is that instead of sorting the output, if you use a trick to keep to calculate them in a sorted order, we can skip the sorting. To do that, we start with the last column and then calculate the sums one by one all the way back to the first one. Then we do the anti-diagonal, and then we do all of the rows. So in that way, all of the ones that are not matching with the main diagonal are kept in a sorted fashion. And to keep them, we can use a list or an array that keeps track of its length, something like that. Now let me give you a sample source code that does the job in C language. You can see just the variables are defined, and we read the input, just reading a matrix in a nested for loop. Then this is the main diagonal calculation. Afterwards, we just have to do the sum over the columns. We start with the last column, go all the way back to the first column. Then we do the anti-diagonal and then the rows. And the ones that do not match in all of the cases are just kept inside the inside an array res, in which the length of it is taken care of, is kept carefully. And then finally we just print the results. So that's it about the magic square problem. I hope you enjoyed watching this video, and have a good day.